Everybody for coming. Warm welcome to my pre-defense. Defense part one. For those who are not in the computer science department, just think about it that way. I'm going to be talking today about the Combinatorial Nullstellensatz. Don't be impressed by the German origin name. It's very elementary. Everything should be accessible, and I invite questions as we go along. So if there's something that's not clear, ask question, and I'm going to try and do my best to answer these. All right, so during this talk, there's going to be two take-home messages. All right, so the first one is that if you mix inside the pot of mathematical investigation the algebra of polynomials, just polynomials, and a little bit of probability theory, what comes out is not only the algebra of matrices, spectral analysis, but the algebra of tensors also comes out. All right, so I'm going to try and convey how this happens during this talk. And a measure of success is, at the end, if I ask you a question and you can answer it, then I succeeded. Otherwise, I completely failed. So that's the first take-home message. The second take-home message is going to be that the mechanical act of expanding out polynomials. You know, we are taught in school that a plus b squared is a squared plus 2ab plus b squared. That mechanical act actually can be converted into a machinery for solving combinatorial problems. And the problem you should keep in mind is the subgraph isomorphism problem. So I'm giving two objects, and I'm asking, is there a copy of that object in my bigger object? So I'm going to show, building on work that's been done before, how you can turn expanding a polynomial into a solution of your traveling salesman problem or Hamiltonian path problem. All right, and I'll explain as we go how you do that. All right, now let's get a sense of our motivation. How did we get here? All right, so 4 years ago, I started this project where what we wanted to do is find good descriptors for graphs. So graphs are a collection of vertices and edges. And the way to think about them is collection of cities and their roadmaps. So I tell you, there's a way of going from New Brunswick to Princeton. Here's the roadmap, here's the distances. And what you want to be able to do in the end is recognize whether a city in Germany has exactly the same structure as the city we're looking at here in New Jersey. All right? And maybe they're not quite the same, but you want to know that there's a collection of towns which have exactly the same structure with some smaller subset of the street patterns in New Jersey. Now this problem is known to be NP-hard, so it's hopeless to hope to solve this in polynomial time. So we're seeking for some approximation algorithm. So typically in computer vision, recognizing faces, matching features often reduces to that. So having good ways of solving that problem is important. So what we set out to do in the beginning is find spectral invariants. And spectral invariants are coming from computing eigenvalues and eigenvectors. So if these two objects have the same set of eigenvalues, then somehow they're similar. However, eigenvalues don't quite tell you all the story. There are many graphs which have the same set of eigenvalues, which are not the same structure. So there's been a lot of work to try and remedy that difficulty. So think about this scenario. How do you solve this problem? So here is typically the method we were investigating. So somebody gives you a parachute. And he gives you two parachutes. He tells you to compare the two parachutes whether they look alike. So you walk through the parachute. It's very large, trying to tell whether these parachutes are the same. And it's much easier to do that if you were to inflate the parachutes. So if you inflate the parachute, you can look at the shape and say, wait a minute, this inflates into a bubble, this one inflates to a rectangle, so these parachutes cannot be the same. What we do is the same for graphs. So you start with a graph, which we describe as a matrix, and then we try to tell them apart. If we fail to do it, we inflate them to hypergraphs, and then we try to do them apart using spectral analysis, eigenvalues and eigenvectors. Now it turns out that eigenvalues are well defined for matrices. How you're going to define eigenvalues for tensors is tricky. Now there's been a lot of work on doing that, and there are good news and bad news. The first good news is, yes, and the work of Lee Kun-Ki, Lek-Heng Lim, Sturmfels, and Dustin Cartwright, they actually showed that it's well defined to talk about eigenvalues for tensors. The bad news is that they're exponentially many. So you want to solve something efficiently, and the invariants you use have exponential size. This is just as hard to go through them as to look at all possible permutations. So eigenvalues of tensors seems to be not the way to go. So we said, let's look at a different approach for solving that problem. And luckily, we were beaten to the punch by Messner and Bhattacharya, who were sort of investigating the same problem from a different perspective. So in 1990 and 1994, Bhattacharya and Messner were investigating a generalization of an algebra called the Bose-Messner algebra used for constructing codes, good error correcting code. And when they did that, they introduced a new generalization of linear algebra. So you want to multiply matrices, and their algebra told you how to do that. What they suggest is how to multiply tensors. All right? So we wanted to build on that somehow. In 1995, Bhattacharya wrote a follow-up paper on their ternary algebra, and he said, we get a new Fourier transform, which is provably not reducible to the 2D Fourier transform. All right? But in the same paper, he raises this very important question of how do you do spectral analysis in their algebraic framework? So in our work, trying to follow up on spectral invariants, not necessarily computing eigenvalues, we wanted to answer the question of how do you do spectral analysis? And the good news is, yes, you can do spectral analysis, and the invariants are not exponential size. But it's not as strong enough, it's not as strong to buy you the to distinguish the graphs completely. All right? So that's the first part. For the second part now. Well, by the time we did this, we realized that you're back to solving a system of polynomials equation. So you leave a problem which started with polynomial constraints. You're back to a new set of polynomial constraints. You haven't really solved your problem until you deal with polynomial constraints. So following on the work of Alon, where we took the title of Combinatorial Nullstellensatz, we're going to describe that, well, if you start with polynomial constraints, if you expand out the polynomials and you're very careful about which polynomial you pick, you can indeed solve your problem. Alon had provided existence criteria, and he asked in his paper whether you can turn his existence criteria into an algorithm. And this is what we succeed in doing. And I think there's some nice follow-up work that can be done into turning these into lower bound or upper bound results. So we prove an upper bound, and we're hoping to achieve a lower bound result. All right, so far so good. If there's any question at any point in time, stop me. So this is the overview. So now that we've given the overview, let's run into the mathematics. I told you that polynomials are the bread and butter we're going to start with. You start with a polynomial, and linear algebra should follow naturally. You shouldn't have to talk about matrix multiplication and matrix addition. Completely from the algebra of polynomial, this is going to come about. So how should this happen? Well, the first tool is the Lagrange Interpolation. Lagrange Interpolation formula is this amazing tool from polynomial which mimics a list. So what a list does is says, the first entry of my list, I put this value. The second entry of my list, I put this other value. The third entry of my list, I put this other value. What Lagrange interpolation allows you to do is to construct a list using a polynomial. So you store your values, so these are our values, and here we're storing a two-dimensional array. What is beautiful about Lagrange interpolation compared to just storing a list is that you can actually query your polynomials at values that were not in your list. If you store a list of 3 integers, you can only query your array at index 1, index 2, or index 3. However, if you use a polynomial, it actually makes sense to query your list at index 1/2. And that turns out to be very interesting because somehow, when you encode things as a polynomial, no matter where you query your list, 3 points would determine, 4 points are going to determine the 3 points you have in your list. So that's a very useful feature we're going to explore. How do we do it for matrices? We start with an n by n array. And as algebraics, we are going to index the array, not using integers, but using roots of unity, because it's very convenient for us. And the beauty is that this formula buys us right away the so-called fast Fourier transform. So if I expand out this polynomial, I get this expansion here, which corresponds to the polynomial which stores the entries of the matrix, and these are the column matrix of the discrete Fourier matrix. All right, so the idea is if I plug in here roots of unity, I get the entry, the corresponding entry of the matrix. So far, so good? All right. So once we have that, what does it buy us? Well, the thing it really buys us is the fact that all of a sudden, expectations over random variables is going to become matrix multiplication. How is that happening? Well, think about two polynomials, and you're free to pick any one you want. You pick two polynomials, and you pick now a set of random variables. So you have two random variables. They come in a pair. And these random variables can take roots of unity. Omega is the collection of kth roots of unity. All right? So now, if you say these are my random variables, and I associate with them a joint discrete probability distribution, then uncentered covariance, which is just correlating two random variables, has this formula. This is a formula for expectation of the product of two random variables. Well, if you pick your joint distribution to be the identity matrix, this is a formula for matrix multiplication. So matrix multiplication is a correlation measure for two polynomials. All right? So once you see things from this perspective, it becomes easier to think about how you would generalize matrix multiplication. And this is really what the work of Bhattacharya and Messner really did. All right, so let's look at things from this perspective and see what it buys us. Well, it buys us that if you have these two polynomials, you compute their correlation, what you get is the multiplication of these matrices. That's the first observation. All right? Now, why would Bhattacharya and Messner end up with a ternary algebra? Well, they end up with a ternary algebra because they're computing the correlation of three random variables. If you have two random variables, you do the correlation, you're doing matrix multiplication. However, if you look at three random variables, where this one is the first one, and it's a polynomial now in three variables. This one is a polynomial and three variables as well. If you correlate these using expectation, you get now this new product, which we're going to call ternary tensor product. All right? So far, so good. You input three polynomials, you get a new polynomial as expectation, and this is going to give us our algebra of polynomials, of tensors. Right? So the reason why we have a ternary algebra is just because we're correlating three random variables. If you wanted to look at tensors of order 4, then you would be correlating 4 random variables. So this is the sprinkle of probability theory. All right? Okay, so let's continue. Now that we've seen the algebra, let's actually define what's happening inside the circle. And inside the circle, here's a picture you should have in mind. So each one of these are cubes, three-dimensional cubes, where you had matrices, turn them into cubes. And each one of the entry here is a correlation coming from each one of these. So this is going to feed the row tubes. This guy is going to feed the depth tubes. And this guy is feeding the column tubes. So every entry here can be thought as the correlation of the corresponding row tube, depth tube, and column tube, so that every entry is a correlation of these vectors. And if we want to think about it in terms of probability, you're picking these vectors, these lists, as we said, stored in polynomials, and computing their correlation values. All right? So this is the basic picture we want to keep in mind. When you generalize, when you start in linear algebra, this guy isn't there. You're just correlating rows and columns. But if you're working with tensors, you're adding this new direction, and you're correlating these guys to get the output. All right, so that's the algebra. What now? If you want to do spectral analysis, there are two ingredients you need. First, the idea is to find a decomposition. Just as matrices, you decompose a matrix into correlation measures. You want to say, there are variables which are independent, which do not correlate. When I scale them, I get A. So the first ingredient we need is orthogonality. So let's get orthogonality. For matrices, we say a matrix Q is orthogonal if Q times Q transpose is identity. It's the Kronecker delta. And another way of saying it is saying I have a set of vectors, n vectors, which do not correlate. If I take two distinct vectors, the correlation measure is 0. If I take the same, the correlation measure is 1. So how should we do this for tensors? Well, we say once you have the algebra, algebra tells you what the orthogonality should mean. So let's actually use our algebra. Algebra tells us, well, you have to multiply Q and its transpose. What are transposes here? Transpose for a tensor is the cyclic permutation of the indices. What that really means is you want an operation that can turn this vector into this one, into this one. And the cyclic permutation of the indices does it for you, so that what we proposed in 2011 was that let's look at these as orthogonality. Now I have to convince you that such objects exist, that it's not a fluke, that for every constant n greater than 1, there are such objects, and they're not rare. Otherwise, there's no hope for doing spectral analysis in general. So how do we convince you of that? Well, to convince you of that, I'm going to show an algorithm for actually producing these guys. And that algorithm is going to mimic a lot what Gram-Schmidt does. Right? So let's think about what Gram-Schmidt does. So Gram-Schmidt takes a set of vectors and produces an orthogonal set if these vectors were linearly independent. Now there's something very annoying about what Gram-Schmidt does. Gram-Schmidt is actually not invariant on the permutation of the rows. That is, the set of vectors that Gram-Schmidt produces actually depends on the order of the vectors you have in it. So that feature, that annoying character, you can remove it easily, and here's how. Just take all the n choose 2 vectors. This is what we're doing here. We're taking all n choose vectors. And then we subtract from the Hadamard product. So Hadamard product of vectors is entry-wise multiplication of the vectors. So, the natural addition for vectors is adding the entries. You get 2 vectors, you get another vector. The Hadamard product does the natural thing for multiplication. It takes 2 vectors as inputs, multiply entries, and obtains another vector. So we said take the n choose 2 vectors, you compute their Hadamard product, and if they were orthogonal, then that means that Hadamard product would have been orthogonal to the all one direction. Right? But it might not be the case, so let's remove the component in the all one direction. We remove it. But by the time you remove it, it's actually not clear how you're going to separate back these guys to obtain Qij. Well, what is very convenient is that by the time you consider these Hadamard products, to get the Qij, all you need to do is solve a system of linear equations. And where are the linear equations coming from? Well, entry-wise, here's what we said. It's Qik times Qjk. We apply the logarithm on both sides. Then multiplication becomes addition. You pick n constraints here, the n constraints, and then you write linear combinations, symbolic linear combination of the n choose 2 minus n others, and this is a symbolic linear system of equation. To check when the system of equation admits a unique solution, you just compute the determinant, and the determinant is a polynomial which would not be identically 0. So I'm saying this is a linear system of equation which specify all the orthogonal matrix you can get by this. All right, so this is Gram-Schmidt in a way that the output is invariant on the permutation of the colors. All right, we do the same thing. We do exactly that algorithm for tensors. So we said the orthogonality picture which we propose is essentially saying if you take the tubes, and since there's n squared tube, you take the tubes and you correlate them. You want to have 0 when they're different. These are the indices we're looking at. And we essentially apply the same algorithm. We say, well, we want the correlation to be 0, so we apply the logarithm to the entries, and we subtract the component in the all one direction. By the time you do that, we show that there exist many solutions to your system of linear constraints. All right, so this actually buys us that indeed orthogonal tensors exist. The second ingredient now that you have orthogonal tensors is the notion of scaling. So let's now get what the spectral tensor means in the algebra of polynomial. Right. So right before we talk about scaling, let me actually introduce this notion of conjugates of complex numbers. So the reason we're going to need conjugate of complex numbers is we want to have a definition for tensors of hermicity. What does it mean for a tensor to be Hermitian? And hermicity is actually very important in the arguments we're making. So for a real number, the square is always positive. This is a useful feature. However, if you're working with complex number, that statement is no longer true. If you take I squared is -1, so square is not always positive. Now, if you say you want something that's always going to give you the absolute value squared, then you need to multiply the number by its conjugate. All right? And what the conjugate is really doing is multiplying z, taking the complex number, the absolute value of z. This here is e to the argument, and exponentiating it with a root of unity, which is the second root of unity. So that's what we say by, this is what we mean by saying, everywhere where you see negative I, turn it into minus negative I when you're doing the conjugate of a complex number. So what I want to define here is an operation which would ensure that the cubes are always positive. If you want the cubes to be always positive, how should you modify conjugation? And the argument is you do something similar. You take your complex number, take the polar, the e to the argument, and then raise it to the appropriate root of unity. And here the root of unity that we'll use is going to be the third root of unity. What is nice about it is that it has the behavior you would expect, in that if you multiply f times f conjugate, you get the absolute value squared. If you sum all of those, you get the L2 norm. If you wanted to do this for p, arbitrary p, and use this definition of conjugate, summing all the conjugates gives you the LP norm to the power p. So this mimics the behavior of the L2 operator under the conjugate inner product. And we actually want that to talk about hermicity. Why? Well, here's the spectral theorem. Here's the spectral theorem in the language of polynomials. It says the following. If you give me a polynomial in two variables, and you make sure that the polynomial has degree at most n minus 1, this is to make sure that the degree of this polynomial is no bigger than n minus 1. Then, you give me such a polynomial and you ensure that the polynomial, the conjugate transpose is equal to the polynomial. So this is the conjugate. This is the usual conjugate transpose, right? So you conjugate and then you flip the variables. If you give me a polynomial which essentially corresponds to a Hermitian matrix, the spectral theorem says you can separate, you can write this thing in a way that you separate the variables. What the eigenvectors are doing is separating the dependence on x0 and the dependence on x1, and saying that the corresponding variables are independent. So in the language of polynomials, the way you say this is that the identity polynomial, the polynomial corresponding to the identity matrix, and the polynomial corresponding to A are in the intersection of the ideal generated by Qx0r and the conjugate of Qx1r. So, right, and where I is the identity polynomial. So, what we're really saying is that what the spectral theorem buys us is that we can separate the dependency on the variables. Okay, so what we were able to show is that this theorem actually holds for tensors. So the strong version of the spectral theorem for tensors, it says, if you give me a polynomial in 3 variables, and the degree is no bigger than n minus 1, such that when you conjugate and flip the variables, so here the transpose is cyclic permutation of the indices, you can indeed separate the dependency in the variables. But look, we're not separating one by one. We're taking pairs. Right? So in the previous one, there was dependency only on one variable. There's qx1, qx2, and it's the same polynomial. But for tensors, there's a dependency on two variables for each, and it's the same polynomial. So it says you can separate out the variable dependency, but not completely. So you should think about these as eigenmatrices. Whereas in the first case, these were the polynomial describing the eigenvectors. In the second case, what we're really looking at are polynomial describing eigenmatrices. And now this is really what's buying us the fact that there are not too many of them. They can be at most n eigenmatrices. So if you get hold of these eigenmatrices, perhaps you can have strong invariants. So we show, and I skipped the proof for the interest of time, so we show that indeed the spectral theorem is true, as stated, and you can prove it using Brauer fixed point. And that's why we needed the notion of norm. To do Brauer fixed point, you need a notion of norms on this space.
It's an existence proof.
Yes, well,
Yes,
it's not constructive. I actually admit the proof that we produce is an existent proof. It's not constructive. However, we were able to prove a constructive version of a weaker theorem. And the reason really why it's hard to prove for the spectral form, I mean, definitely for eigenvalues, it's known. There are constructive proofs of going about it. It goes by via the characteristic polynomial. The reason why it's hard to do the same thing for tensors is these conjugation operations. They're actually not algebraic. So if you use algebra to do them, you can't get hold of them. So you have to weaken the theorem in order to be able to prove it constructively. All right, so let me show you how we weaken the theorem. So we said this is a spectral theorem for matrices. Find an orthogonal set, a set of vectors which are orthogonal. If you scale each one of these orthogonal vectors, you get A. And the matrices should be diagonal. So star square is squaring the entries of the matrix. So it's a Hadamard power. We had Hadamard product. This is the Hadamard power. So we're saying here that this means that if you correlate your variables, you get the entries of A. But if you did not scale these variables, you would get the identity matrix, which says our variables are not correlated, but when you scale them, they give you A. All right? So now we're saying, well, it's hard to deal with these conjugation. Let's actually put these two guys together. So you can do that using Hadamard product. You get Qij. And say, well, we don't care that these entries be the same for all the vectors. So this form is a weaker form of the spectral theorem, and this one is easier to prove using algebra. So what we show is that for tensors, this is the corresponding equation. These are the correlation identity. These are the diagonal entries, and this is how you scale them to get A. So we can show that indeed this decomposition is completely determined by the minors, whereas the strong form of the spectral theorem, we only have an existence result. So computing this exactly, we don't know how to do. But computing this exactly, we have a very good idea how to do. And it reduces to computing the spectral decomposition for 2 by 2 by 2. So the minors are going to buy you this. So this is a recent result. We haven't really explored in detail what it actually buys you in the case of matrices. You can think about this as an approximation algorithm for computing eigenvalues and eigenvectors. All right, so what do we want to do now? So I think at this point we're ready to shift gears because I told you that we're back to algebraic constraints. So somehow you have to say something about how to solve algebraic constraint. And the inspiration comes from the classical paper of Noga-Alon. So Noga-Alon proves this theorem, which was slightly generalized this year. And his theorem says that if you give me a polynomial and you assure me that the coefficient of the leading term is not 0, all right? So the coefficient of this term is not 0. Then for any set in the field, any subset in the field, which which has enough elements, he can find you a point where the polynomial evaluated there is not going to be zero.